Welcome to the deep dive. You sent us some really interesting material, Nvidia CEO Jensen Huang's latest keynote.
Yeah, quite the presentation.
So our mission today is, as always, to pull out the key insights, the stuff that really matters, and get you up to speed fast. We're diving into Nvidia's big picture for computing's future.
Right, focusing on their plans for AI, robotics. It's ambitious stuff.
Definitely. And uncovering how they're not just predicting markets, but actively, well, creating them.
And I think what's really vital to get from the start is this isn't your typical product launch announcement.
No.
No, it feels much bigger. It's like they're trying to fundamentally reshape the whole infrastructure of how we compute things.
Okay, infrastructure. Let's unpack that. Maybe we can start by looking back a bit. NVIDIA's been around 30 years.
Right, and people mostly know them as a chip company, a GPU company.
But the story's bigger than that, isn't it?
Oh, absolutely. I mean, look at CUDA back in 2006. That was a seismic moment.
How so?
Well, this parallel computing platform, it wasn't just, a little bit faster. It completely changed the game for tackling complex problems, harnessing all that parallel power.
Initially for graphics.
Exactly. Started with graphics, but the potential was way beyond that.
Yeah.
Laid the groundwork.
Groundwork for what came next. Because by 2016, they seemed to realize AI needed something totally different.
Yeah, that was the realization. AI demanded a complete rethink, a reinvention of everything, the processor, the software, the whole system.
That sounds huge. How do you even start something like that?
Their answer was the DGX-1. They announced it at GTC 2016. And it's funny looking back.
Why?
Because honestly, at first people didn't quite get it. There wasn't a flood of orders. But that very first DGX-1, they donated it to OpenAI.
Ah, okay. So that was the spark.
You could definitely say that.
Yeah.
Looking back, it was a crucial catalyst for the whole AI explosion we're seeing now.
It's fascinating how that initial maybe confusion turned into this whole new way of computing.
Right. We were moving away from that hyperscale model, big tasks on a few powerful machines,
Towards
needing lots and lots of processors all working together, communicating intensely. Huang called it an east-west network.
Right, highlighting that side-to-side communication between machines, not just up and down.
Exactly. And if you connect the dots there, the Mellanox acquisition in 2019 makes perfect sense.
Because Mellanox specialized in that high-speed, low-latency networking.
Precisely. They had the missing piece, the tech needed for that super-fast east-west communication, the highways for all that data.
Okay, so the big picture emerging is the modern computer isn't just the box on your desk or even a single server.
It's the entire data center, functioning as one giant unified computer that completely changes how you think about building things out, the infrastructure.
And speaking of infrastructure, something that really stood out was NVIDIA sharing a 5-year roadmap. That's unusual in tech, right? So secretive, usually.
Very unusual. But Huang explained it's not just showing off future tech. It's, necessary.
Necessary how?
For planning. Think about building these new AI factories he talked about. You need land, massive amounts of power, huge financial backing. You need years of lead time.
Right. So they're positioning themselves not just as selling tech, but as a foundational infrastructure company.
Like the companies that built the power grid for the first industrial revolution.
Yeah.
Or the ones who laid the cables for the internet.
That's a powerful analogy. And now it's an infrastructure of intelligence.
That's the term he used. AI woven into everything, almost invisible. Which brings us to these AI factories.
Okay, what are they exactly? Different from regular data centers?
He argued yes. Their main output isn't just storing data, it's producing tokens, the building blocks of LLMs, generative AI.
So the success metric shifts.
Right. It becomes tokens produced per hour, a direct measure of AI output.
And the market size perception. It's just exploded, hasn't it? From, $300 million back in '93?
To potentially trillions now, focused on this AI infrastructure. It puts their whole journey into perspective.
Okay, so let's dig into the core of this vision. Accelerated computing and AI.
Yeah, and it's not just those two things separately, but how they fuse together. That's their strength.
And he kept emphasizing something often overlooked, didn't he? The libraries.
Yes. The CUDX libraries, he really hammered this point, this huge collection of algorithms, software. It's the unsung hero. He basically said NVIDIA is unique in how much they focus on libraries.
Calling them the bedrock for all their innovation.
Pretty much. And he made a point of saying everything they showed, all the cool demos, wasn't just art, it was simulation. Driven by science, by AI, built on those libraries.
Like the real-time graphics demo with the new GeForce RTX 5060, that was pretty mind-bending.
It really was. The idea that they're only actually rendering 1 pixel in 10.
And AI guesses the other 9 perfectly.
Using DLSS, neural rendering.
Yeah.
He said it took 10 years to get there. That's a fundamental shift in graphics.
It feels like a full circle. GeForce brought CUDA to the masses.
And now AI is transforming what GeForce can even do. It creates this amazing feedback loop.
Explain that loop.
Okay, so big install base of CUDA hardware attracts developers. They build specialized libraries. Those libraries enable cool new apps. Users benefit. They buy more computers. The CUDA base grows and repeat.
Right, and this highlights the difference between old-school general-purpose computing.
Write code, compile it, run it on a CPU.
And this accelerated approach. You need a different way of thinking to get those massive speed-ups.
Totally. You have to deeply understand the specific problem domain you're trying to accelerate.
And the examples of those CUDX libraries were just, wow. The range was incredible.
Wasn't it? CuPy for numerics, Ariel for AI on 5G, 6G radio signals.
PARS for genomics, MONAI for medical imaging, Earth-2 for weather.
And KU litho for computational lithography. That's huge for chip making itself. Getting 5070X speedups there, working with TSMC, ASML.
Imagine speeding up chip design that much. That's kind of meta.
It really is. It shows their strategy. Build the tools, accelerate specific fields, and basically create or expand markets by making hard computational stuff easier.
Speaking of expanding markets, telecommunications seemed like a big focus.
Yeah, the shift to software-defined RAN. Nvidia's platform is now hitting performance levels that rival custom chips, ASICs.
Which opens the door to layering AI right onto 5G, 6G networks.
Exactly. And they listed major players partnering with them: SoftBank, T-Mobile, Nokia, Samsung.
Another frontier mention was quantum computing. Still early days, right?
Yeah.
The NISQ era.
Right, noisy intermediate scale quantum. But Huang made a bold prediction.
Which was?
That all future supercomputers will have QPUs, quantum processing units, alongside CPUs and GPUs.
And NVIDIA's role.
They're building this hybrid quantum classical platform, CU Quantum. Their GPUs handle stuff like preprocessing, error correction control, essential tasks in this early phase.
Okay, let's pivot slightly to AI itself. How did Huang frame its evolution?
He traced it back, starting maybe 12 years ago with perception AI.
Pattern recognition, basically, like seeing images, hearing speech.
Exactly. Then, the last 5 years or so, we've seen the rise of generative AI.
Creating new stuff, text, images, code.
Right. He described AI almost like a universal translator or approximator, learning complex relationships in data.
And ChatGPT really brought that one-shot AI idea to the forefront, text in, text out.
Definitely. But he stressed that true intelligence is more than generation. It's reasoning.
Solving problems you haven't seen before. Thinking step by step.
Yeah, simulating options. Things like chain of thought, tree of thought, those are key advancements for reasoning.
And building on reasoning leads to agentic AI.
Right. AI that combines perception and reasoning. You can understand a goal, make a plan, think about consequences, and then act. Digital robots, basically. Understand, think, act.
Then the next step is physical AI, understanding the real world.
Exactly. Grasping physics, inertia, friction, objects continuing to exist even when you can't see them.
Like the example of generating training videos for self-driving cars.
Yeah, that showed a glimpse.
Yeah.
The ultimate path seems to be reasoning leads to generation, leads to physical robots interacting with the world.
Which brings us neatly to the hardware needed to power all this, the next-gen platforms.
So Hopper was huge for AI training, but the new system, Grace Blackwell, is really tuned for inference.
For the AI thinking part, the real-time response.
Right, and a key thing about its architecture is how it scales. It can scale up, making one massive computer beyond normal chip limits, which is incredibly hard.
And scale out.
And scale out, connecting tons of these systems together seamlessly.
And these are already in production, despite the complexity.
Apparently so. Key partners are building systems now. CoreWeave was mentioned, plus the big cloud providers adopting it.
And there's already a next step coming soon, GB300.
Yeah, Q3 this year. Same basic design, but 1.5x the inference speed, 1.5x the memory, twice the networking in the same footprint.
The performance jump he quoted was staggering. One node matching the entire Sierra supercomputer from 2018.
Which had 18,000 GPUs. It's a 4,000x increase in 6 years. He called it extreme Moore's law. It's not just transistors shrinking anymore, it's architecture.
Driven by things like connecting two Blackwell chips with that advanced TSMC process.
CoASL, yeah. And that NVLink switch, world's fastest interconnect.
moving more data than the entire internet's peak traffic.
That's the claim. And the NVLink spine connects all 72 GPUs in a rack with 2 miles of cable, letting every GPU talk to every other one simultaneously.
Wow. So the whole rack is essentially one giant processor.
Exactly. And it needs serious power, 120 kilowatts and liquid cooling. It really reinforces that shift away from just servers or data centers.
Towards building these AI factories.
Purpose-built for churning out intelligence. CoreWeave, Oracle Cloud, that huge XAI Colossus project. Massive bets on this model.
The manufacturing video really brought home the complexity. TSMC wafers, billions of transistors, testing, packaging, robots at Foxconn, liquid cooling.
It's an incredible feat of engineering and collaboration, especially highlighting the ecosystem in Taiwan.
Which led to the announcement about building a giant AI supercomputer in Taiwan, right?
Yeah, big collaboration. Foxconn, the government, Nvidia, TSMC, aimed at researchers, startups, big companies there, including supporting TSMC's and Foxconn's own robotics work.
And we saw systems from all the big Taiwanese players, Pegatron, Quanta, Gigabyte, Asus, all designed to link Blackwells together.
And it's more than just the hardware, right? It's the system design, the software. Years of work, hundreds of partners, huge investment.
To make this kind of advanced infrastructure potentially more accessible, they introduced NVLink Fusion. What's the idea there?
It's about enabling semi-custom AI infrastructure. Not just semi-custom chips, but whole systems.
Why is that needed?
Because different AI workloads need different mixes. Sometimes more CPUs, sometimes more GPUs, sometimes specialized custom chips, ASICs.
And the missing link was connecting these different pieces efficiently at scale.
Exactly. NVLink Fusion is designed to be that high-bandwidth interconnect for scaling up diverse systems. It offers different ways to integrate.
Why?
You can use a full NVIDIA platform. Or you can plug in your custom ASIC using an NVLink chiplet. Or even integrate NVIDIA tech into your custom CPU using an NVLink interface.
So if a company builds a specialized AI chip, this lets them connect it into the broader NVIDIA ecosystem.
Right. They get access to the NVLink infrastructure. Connects perfectly to Spectrum-X networking, its industrial strength, huge partner support.
Who are the partners?
Semi-custom providers like LCHIP, Astera, Marvell, MediaTek, CPU makers like Fujitsu, Qualcomm integrating NVLink, and IP partners like Cadence, Synopsys.
Okay, shifting to new products. DGX Spark, what's that?
It's in production, coming soon via Dell, HP, Asus, etc. Think of it as a personal AI cloud for developers.
Personal, how powerful?
A petaflop of performance, 128 gigs of memory. Desktop form factor. Remarkably, that's similar performance to the original DGX-1, the big data center box.
Wow, so bringing that power down to the developer's desk.
Exactly. He even joked everybody can have one for Christmas. Probably a bit optimistic, but it shows the direction.
And the DGX station, another personal system.
Yeah, a personal AI supercomputer, capable of running massive trillion-parameter models locally from a standard wall socket. Well, maybe a beefy one.
He mentioned kitchen compatibility with a microwave caveat.
Right. But the key is, it uses the same programming model as the giant systems. Develop locally, deploy at scale. These are AI-native computers.
Not necessarily designed for old-school IT like x86 apps or Windows.
Not primarily. They can run them maybe as APIs for other apps, but they're optimized for this new generation of AI software.
Okay, but what about bringing AI into those traditional enterprise IT environments? That seems like a huge challenge.
It is. And NVIDIA's approach is to kind of reinvent the lower layers, compute, storage, networking, to support these new AI capabilities, especially agentic AI.
The digital workers idea, AI agents doing tasks like marketing, research.
Exactly. Reasoning, using tools, working with other AIs. He talked about addressing labor shortages with these digital agents, even using them internally at NVIDIA for software engineers.
It sounds like you'd need new management tools, like HR for digital workers.
That's the vision. So on the compute side, there's the RTX Pro enterprise platform and Omniverse server.
What do they do?
They're designed to run everything existing by 86 apps. Hypervisors like VMware, Kubernetes, Citrix, but also be the powerhouse for these enterprise AI agents handling text, graphics, video.
And the networking gets an upgrade, too.
Big time. The new CX8 chip family, high-performance switches. Inside the RTX Pro server, CX8 connects the 8 Blackwell RTX Pro GPUs via PCIe.
Giving them
800 gigabits per second of bandwidth just for that east-west GPU communication.
Yeah.
Each GPU basically gets its own super-fast network connection.
So for these AI factories, the performance metrics change, right? Not just FLOPS.
Right. It's about throughput tokens per second, 1 gigabit per second, 1 terabit per second, 1 gigabit per second. 1 terabit per second. 1 gigabit 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 and latency or interactivity tokens per second per user.
Getting both high throughput and low latency is tricky.
Very. It requires clever software to manage how the GPUs work together, parallelism, batching, speculative decoding, lots of computer science.
And the performance gains are significant.
He showed the Blackwell server being 1.7x faster than Hopper H100 on a standard model like Llama 70B, but then 4x faster on an optimized model, DeepSeek R1. That suggests big software breakthroughs too.
Okay, let's talk data. AI needs to query unstructured data, not just SQL databases. How does that work?
That's where the new AI data platform comes in. Humans use SQL for structured data. AI needs to understand semantic meaning in unstructured text, images, etc.
So a new kind of storage.
And a new query system, Nvidia AIQ or IQ. The idea is future storage will have GPUs sitting right on top of the storage racks.
Why? What do the GPUs do there?
Compute-intensive stuff needed for understanding unstructured data. Creating embeddings, indexing it, searching, ranking results. It's all part of IQ.
And this relies on having good AI models.
Definitely, including fine-tuning open models with your own safe, secure data. He mentioned their Llama Neutron model as a top open-source reasoning model.
And the IQ system itself is faster?
The retrieval part, yeah. 15x faster, he claimed, with 50% better query results. The blueprints are open source, and storage partners like VAST, Dell, IBM, NetApp are integrating it.
We saw that vast sales agent example.
Right, leveraging these capabilities.
Then there's AI ops. What's that layer for?
Managing the whole AI model lifecycle in the enterprise. Curating data, fine-tuning models, evaluating them, putting up safety guardrails, securing them.
And Nvidia provides
Libraries and models for that ecosystem. They're partnering with specialized AI ops companies, CrowdStrike, Taiku, Red Hat, Elastic, lots of names.
the goal being to let companies add AI without ripping everything out.
Exactly. Integrate AI into existing workflows and infrastructure.
Okay, let's shift gears to robotics. Agentic AI gives us digital robots, but we need physical ones too.
Right. And the starting point, according to Huang, is learning in a virtual world that obeys the laws of physics.
Which requires a really good physics engine.
Enter Newton. Developed with Google DeepMind and Disney Research, he called it the world's most advanced physics engine. It's GPU accelerated, differentiable, which is key for AI learning high fidelity, real time.
And it's being open source.
In July, yeah. And integrated into platforms like Muoko and Nvidia Isaac Sim.
The demo of simulated robots slipping in sand, that wasn't just an animation.
No, that was the actual robot control software running inside the simulation, reacting to the physics. The goal is train the AI there, then deploy to the real robot.
And the platform for this is Isaac Groot, like the one for self-driving cars.
Exactly the same idea. 3 parts.
Right.
Simulation in Omniverse, training on big systems like GB2300, and deployment software with Isaac Groot.
Like Mercedes using their self-driving stack.
Right. But he stressed its open partners can use just the pieces they need. The robot deployment starts with a new processor, Jetson Thor.
And Isaac OS.
That's the runtime. Handles the neural nets, sensor pipelines, controlling the motors. Plus, they provide pre-trained models and tools. Isaac Groot N1.5 is already open source, apparently got lots of downloads.
But getting enough training data for robots is hard, right?
It's a huge bottleneck. So they're using AI to help amplifying human demonstrations via teleoperation.
And this Groot Dreams blueprint, what does that do?
It's built on their Cosmos physical AI models. The idea is to generate synthetic training data at massive scale. You fine-tune Cosmos with some human demos. Then you prompt it with Dreams' desired future states. Cosmos reasons about the best ones, and Groot Dreams generates the detailed 3D action steps to get there.
So the robot can learn lots of new skills from just a few human examples.
That's the goal. A small team does the work of thousands doing manual training, using AI to teach AI robotics.
It sounds like this whole era of agents needs massive compute for synthetic data skill learning.
Absolutely. And Huang made a strong case for humanoid robotics being key.
Why humanoid?
For brownfield deployment. They can fit into environments already designed for humans, factories, warehouses, homes.
He thinks it might be the only form factor to reach the scale needed for rapid tech progress.
That was his argument. Potentially the next multi-trillion-dollar industry driving huge compute and data needs.
So robotics needs 3 computers: AI learning, simulation, deployment.
Right. And the vision is that everything that moves becomes robotic. Factories are definitely heading that way.
And Omniverse is used to create digital twins of these robotic factories.
Yeah, digital twins of the robots, the equipment, the whole factory layout. So robots can learn to work together as a fleet virtually first.
And Taiwan is leading this, with companies like Foxconn, TSMC, Pegatron using Omniverse.
He highlighted many examples, using digital twins for fab layout, production line planning, simulating processes like soldering, even as virtual gyms for robots.
That sounds like a huge opportunity globally, with trillions being invested in new plants.
Definitely. Using digital twins for planning. Nvidia is even doing it for their own AI factory and simulating cities like Kaohsiung.
So Taiwan is pioneering this software-defined manufacturing with Omniverse.
That was the message. From TSMC optimizing layouts, to Pegatron simulating solder paste, to quanta planning production lines. Even using AI agents in Pegatron to help employees via Metropolis.
It really feels like industrial AI is here, and Taiwan's at the center.
Yeah, he positioned Taiwan as being at the epicenter of AI and robotics. A massive opportunity. Just like GeForce brought AI to the world, AI can now transform Taiwan's electronics industry.
And to cap it off, a new Nvidia office in Taiwan.
Called Nvidia Constellation in Beitho-Shilin. A clear sign of their commitment there.
Okay, so let's try to wrap this up. What are the big takeaways from this deep dive into Jensen Huang's vision?
Well, it's incredibly comprehensive, isn't it? It's a future driven by accelerated computing and AI, but grounded in really understanding specific industry needs.
There's that clear strategic shift towards AI infrastructure as the new foundation.
Right. And the maybe underappreciated crucial role of the CODX libraries as the building blocks for almost everything.
We saw that fascinating evolution of AI from just perception through generation to reasoning, agentic AI, and now physical embodiment in robots.
And the transformative potential across so many areas, but especially manufacturing and robotics, where things seem to be moving incredibly fast.
So hopefully this deep dive gave you a shortcut, a way to grasp this really complex and fast-moving landscape.
And maybe a final thought to leave you with. Really consider the implications of these AI factories he described. And think about intelligent agents becoming part of our daily work, interacting with the physical world.
What new possibilities does that open up? What are the challenges we haven't even thought of yet with this coming infrastructure of intelligence? Lots to chew on there.
Definitely something to keep exploring.
Thank you for joining us for this deep dive.